Alright, hi year 12, this is Mr. Lim again, and this is our second video on equilibrium, on dynamic equilibrium. Okay, so let's have a look at what we're going to be learning. We're going to be learning about the characteristics of reversible reactions. Okay, we're going to be looking at what conditions are required for dynamic equilibrium systems to occur, and then finally, how do dynamic equilibriums actually get established, and what are they, and stuff like that. All right, so that's what we're going to be talking about. So let's have a look. What are reversible reactions? Okay, so reversible reactions are reactions that have with a reverse reaction, so not just reactants going to products, but also products going to reactants, occurs at an appreciable rate. What does appreciable mean? It's like it happens at a rate that is reasonable, so that at some point it will eventually equal the forward rate of reaction. Okay. So just the idea that the reverse reaction can occur, okay, and can occur to an appreciable amount. We're going to talk about the reversible nature of reactions to collision theory. So why in the world would some reactions be reversible and some reactions not be reversible? So let's have a think. It requires both the forward and the reverse activation energies to be reasonably similar, okay, which results in a low delta H. So what does that mean? Let's go draw that out. Okay, so let's have a look. Let's move over here a bit. So, wrong way. Okay, so, come on. Okay, let's have a think. Is that an exo or endothermic reaction there? That is a exothermic reaction. Okay, this is the forward activation energy of the forward reaction. That's how much energy is required to go from a reactant to the transition state. The reverse rate of reaction is this is going backwards. The reverse rate of reaction or reverse reaction is going backwards. This is the activation energy of the reverse reaction, and it's the amount of energy required for products to go to the transition state. Okay, and so these have to be reasonably the same. Now those two here are not reasonably the same. Okay, which results in this delta H being, a reasonable value. So when we say that they have to be reasonably the same, it has to look something a little bit more like this, okay, where you have a very small delta H, but the activation energy of the forward and the activation energy of the reverse are roughly the same, okay? So this allows products to be at the same temperature as the reactants to have enough energy to react and complete the reverse rate of reaction. Okay, so what does that mean? Products at the same temperature as the reactants to have enough energy to react and complete the reverse reaction. So what does that mean? We're going to go through that? Yeah, we're going to go through that now. Okay, so the idea is that the products and the reactants are going to be at the same temperature because generally they're just going to be in the same container under the same conditions. They're going to be at the same temperature. And if you think about a energy distribution graph, okay, this will be for the reactants, and then I'll use a different color for the products, okay. They're going to be at the same temperature. There might be different amounts, right? But if they're at the same temperature, they're going to have this there, right? And if their activation energies are roughly the same, this is the EA of the forward, and let's just say that this is the EA of the reverse, okay, EA of the reverse, then you can have the amount of particles with sufficient energy, whoops, those weren't supposed to be green. You can have the amount of particles with sufficient energy to be roughly the same if you have similar numbers of particles, or even if you don't have similar number of particles, as long as these shaded areas can be appreciable, then it's going to work, right? But if I had an activation energy which was like, all the way up here, and I know that goes off the scale, but you get the idea, all right? If I had an activation energy all the way up here for one of them, then it would never be appreciable. All right, so the black line with the red activation energy would be like, yep, I got all of those with sufficient energy, but there'd be almost none of those for the blue line because the blue line doesn't even get to that point. Okay, so if the yellow line was the activation energy of the reverse, then that would not have an appreciable amount of reactions occurring. Okay, and I've spent too much time explaining that. Let's go on. Okay, so identify reversible reactions from energy profile diagrams. So you should just remember you're looking for a low delta H, small delta H for energy profile diagrams. Would this one have a, would that one be reversible? Yes, it would, because it still has a low delta H. Okay, let's move on. What conditions are required for dynamic equilibrium? So you need to be able to describe an open and enclosed system. So what's an open system? Open systems are when both matter and energy can be transferred from system to surroundings, which means it goes stuff and energy can go in and out of the system, right? Which is not useful because if you lose the matter, then it's going to not be able to react again. So imagine if your reactants turn to products and then your products go away, those products can't turn back into reactants in the same system. So what you want is then a closed system where only energy can be transferred and then the matter is kept within the system. So it can't run away. So the products that are formed have the opportunity to turn back into reactants because they haven't run away, right? What are some examples of open and closed systems? These are just examples of closed systems, closed gas containers and aqueous solutions, because the ions in solutions can't run away. An open gas container is just not going to be a closed system because any products that are formed are just going to escape into the atmosphere, which is not useful. All right. So what is then dynamic equilibrium? Dynamic equilibrium is when the forward and the reverse reaction rates are equal. Okay. So forward and reverse reaction rates are equal. We discussed what you need to have the ability for a reverse reaction to actually occur and for a reaction to be reversible, but when their forward and reaction rates are equal, you've got a dynamic equilibrium system. And at dynamic equilibrium, there's the same number of particles, products and reactants being consumed and produced every unit of time. Okay, so imagine if you've got 100 being produced of products, you're also going to have 100 being consumed of products and go back. And then you're going to have dynamic equilibrium. So over time, every time there's 100 going forward, there's 100 going back, the numbers of particles on either side aren't going to change. That's dynamic equilibrium, where everything stays the same, but they're always consistently changing. All right. How does a system reach dynamic equilibrium? Hopefully this won't take very long to explain, but hopefully you remember the idea that as you have, let's go here. All right, if you have a rate of reaction, what we remembered before is that slowly the rate of reaction will eventually decrease and get to zero. Why would it get to zero? Why would the rate of reaction decrease? Because you've got less concentration of reactants, and that lower concentration of reactants leads to a lower rate of reaction. That was the idea in year 11, that as you proceeded through the reaction, you consumed reactants, which lowered the concentration of reactants, which lowers the frequency of collisions, which lowered the frequency of successful collisions, which led to a lower rate of reaction. That was year 11 stuff. Okay, now we're going to the next level of year 12 stuff, so let's have a look. Let's get rid of all of this first. Okay, so if you have a large number of reactants, they start to react and make products. We knew that. That makes sense. Okay, so large number of reactants, they start to react, make products. As time goes on, the concentration of reactants, that's what we just said, starts to decrease. And the rate of forward reaction decreases due to the decrease in the frequency of collisions and successful collisions and the forward rate of reaction. So that's what we just discussed. That's all year 11 stuff. As time goes on, okay, the concentration of products starts to increase. Okay, And that's because, you're just making lots of stuff. And if it's a reversible reaction, which means that the products have the ability and the energy to turn back into reactants, the rate of reverse reaction increases over time due to the increase in frequency of collisions. Why are they colliding more frequently? Because there's simply more of them, and therefore more successful collisions of the reverse reaction. Okay, so the idea is that you got more products, they're going to react more, and therefore they're going to increase that rate of reaction. So at that point then, because the forward reaction rate is decreasing and the reverse reaction rate is increasing, eventually the two rates of reaction will become equal, okay? Because the forward is dropping down and the reverse is going up. And then stay at those levels as the concentration of reactants and products are constant over time. Because why does the concentration of reactants and products stay constant? Because you don't have any more or less being produced, because you've got the same amount being produced and consumed. All right. So if we were to draw this in rates of reaction graphs, okay, let's say that this red line is the forward rate of reaction. That one goes down, and this one is the reverse rate of reaction, and that one's going up because there are more products being formed. So over time, this one goes up, this one goes down, this one goes up, this one goes down, this one goes up, and this one goes down until they are equal. All right. That is how you would have the rate of reaction over time of the forward and the reverse rate of reaction establishing dynamic equilibrium. Okay, so dynamic equilibrium then has certain macroscopic properties. What does the word macroscopic mean? Okay, the macroscopic properties is the properties that you can observe, right? And they stay constant because those macroscopic properties are linked to the concentration of substances within those mixtures. Okay, and since the concentration stays constant, therefore these macroscopic properties stay constant. Okay, so what kind of macroscopic properties? You've got things like color, concentration or partial pressure of substances, the pH, and things like pressure of the system overall. Okay, those are the macroscopic things that don't change because the concentration doesn't change. All right, and that's it for dynamic equilibrium. A bit longer than I wanted. I'll try and make the next one shorter. Adios.